Welcome to part 4 of thermal spray deposition technique, where we will discuss about the scope of research and also how to plan for the research studies of different materials development by thermal spray deposition route. In this particular talk, I will discuss about the research results on development of two different types of coating. One is thermal barrier coating and another one is typical bioactive coating for implant applications. So, initially I will discuss about the thermal barrier coating. So, as I mentioned you in the last slide that thermal barrier coating is usually applied on the turbine blades and nozzles where you are looking for very high temperature oxidation resistance property, and there you look for a thick ceramic layer on the surface of the substrate, which is nothing but superalloys, maybe nickel based superalloys or cobalt based superalloys for the applications where for the different applications as you are looking for, and that coating is developed onto the surface of the superalloy, and before that you apply a very thin bond coating made of conicroly, which offers the high temperature oxidation resistance property, and that oxide based ceramics offer that thermal barrier property or acts as insulating barrier for reducing the effective operating temperature of the substrate. So, usually this coating is this is known that this particular top coating is applied by electron beam physical vapor deposition technique or by air plasma spraying technique. But each and every technique is having its own advantages and disadvantages. The advantage of air plasma spraying technique over EBPVD is that air plasma spraying technique is more flexible technique. By this particular technique you can have all lateral cracks, and these lateral cracks acts as a kind of acts as the centers where stress can be relaxed very nicely. So, when the component is subjected to like thermal stress, that cyclic thermal stress, then those stresses can be arrested very nicely on the typical plasma spread defective part like lateral cracks whatever are present on the surface. Air plasma spray is quite cheap and easy to operate. You get thicker coating by air plasma spraying than EBPVD, and it is tougher than that of electron beam physical vapor deposition technique. So, you can for having the flexible composition on the coated layer, for having different types of coating, usually people choose the plasma spray deposition technique, prefer to have plasma spray deposition technique to electron beam physical vapor deposition technique. So, it is known that this technique is applied for TBC development. On the other hand, if you talk about bond coat may be developed by plasma spraying process, but when you develop the bond coat by plasma spraying process, there is chance of lot of porosities which are arrested in the bond coat. So, usually what you do is that you develop the bond coat by typical HVOF spraying technique. So, when you develop it by HVOF spray technique, you get very dense coating, and that dense coating is capable of improving the properties of the component to a large extent, because it offers superior corrosion resistance and high temperature oxidation resistance property of the material. So, if you see the temperature because the temperature profile through the coating, because of the application of the coating, you will find that, or maybe designing of the coating, you will find that this is superalloy which is having the bond coat of the thickness 30 to 100 micron. Then top coat thickness is 100 to 3000 micrometer, 100 to 3000 micrometer, and then usually the TGO layer is having maximum thickness of 0.1 to 10 micron. This is nothing but oxidation product, and the temperature increases from the surface, temperature decreases, and then it is minimum at the bond coat and superalloy substrate. So, you will find that this is the combinations, and this is very quite established that people do use these techniques for this specific purpose. Now, if you are interested to develop newer kind of materials for these thermal barrier applications or newer varieties of coatings having tailored properties, then you have to think of choosing superior materials. So, superior materials in this regard include lanthanum stabilized zirconia, or the composites of ETS stabilized zirconia and lanthanum stabilized zirconia, and also you can add different rare earth element to a large extent in the bond coat, and then prepare the bond coat of completely different composition, and then develop it by HVF spraying technique. So, those are the areas where lot of researchers are working, and then newer materials are developed for this particular purpose. So, in this particular research studies, what we do, I will say briefly explain or share some of our research experience on the development of thermal barrier coating. So, where our newer approach was to develop the graded coating instead of the monolithic ceramic coating as the thermal barrier coating, to have the higher toughness and also superior properties of the coating. So, where what we did is that we basically use the cone standard powder as a bond coat, and for top coat, instead of having the ETS stabilized zirconia monolithic coating, we used a combination of ETS stabilized zirconia and cone in a graded fashion, so that near to the bond coat the composition was 90% bond coat plus 10% top coat. As you go ahead, you will find that the composition of the bond coat, percentage of bond coat decreases, and at the surface it is 100% top coat. So, like that we designed the coating and tried to see the effect on oxidation resistance as well as overall service life of the component. So, as I mentioned you that in this particular say any process of thermal spray deposition, your precursor coating precursor may be in the form of powder, or maybe in the form of wear, or maybe in the form of rod. But when you talk about plasma spray deposition process, then naturally the precursor coating precursor should always be in the form of powder. So, particularly in those cases, for example, where we use that ETS stabilized zirconia as powder. So, when you started developing the ETS stabilized zirconia top coat by plasma spray deposition technique, this ETS stabilized zirconia gas atomized powder was used as precursor powder, which contains mostly tetragonal zirconia. A few monoclinic zirconia is also observed. Monoclinic zirconia peaks are also observed. On the other hand, bond coat was cone. So, where we get only gamma as well as few beta peaks were also observed. So, this particular coating was developed by plasma spraying, this coating was developed by HVF spraying. So, the coating design was like that. So, this is a newer approach which we followed. Basically, instead of having the monolithic coating, we had graded coating. So, where 100% conic 70% conic plus 30, 50, 50, and we developed 4 layers. Each layer is having thickness of 80 micron. So, total and final layer thickness was 100 micron. So, bond coat thickness was around 80 micron, and total top coat thickness was around 340 micron, 340 to 350 micron. So, and each layer was having the similar thickness. So, what we did is that we just developed both the kind of coating in order to show the effect of the compositional gradation on the microstructure composition and properties. So, the steps which you had followed, or which is usually followed for this kind of experiment, was that you have to procure powder, then you have to develop the coating, you have to characterize the coating, then evaluation of properties in terms of high temperature oxidation, wear, erosion, hardness, Young's modulus, thermal conductivity, coefficient of thermal expansion. These all properties were evaluated, and finally, we tried to compare the properties of the both coating to a large extent. So, if you see that coating, thermal barrier coating, microstructure cross section, you will find that this particular coating contains lot of porosities as well as the cracks in the lateral dimension. So, those cracks are present because Those cracks, as I mentioned you, they are essential because they basically they acts as a kind of points of stress relaxation. So, whenever these lateral cracks are present, naturally you will find that whatever thermal stresses are developed, they get relaxed very nicely over the cracked points, and because of the very high large stress, actually there is this change in monoclinic to tetragonal to monoclinic structure, and by this structural transformation the crack tip is also toughened. So, during the process itself you will find that etiacerular zirconia gets toughened, and it offers the further improvement in the toughness. So, in the monolithic coating we had this particular etiacerular zirconia layer, and cone-equally layer you will find there is not much porosities because it has been developed by geostraying route, and you get 100% dense coating. In the case where you use the graded coating, there you find that degree of porosities were a little bit lower than that of monolithic coating, and you will find that there are presence of both metallic as well as ceramic component, and ceramic component content increases as you go on increasing from the depth towards the surface because of the change in the composition. So, this is also visible in the extra diffraction profile. So, you will find that that cross section when the microstructure, this kind of coating is subjected to high temperature oxidation, you will find that there is very thin TGO formation at the interface, and TGO thickness is quite low, and that TGO thickness in fact increases with temperature as well as time of the oxidation. So, usually you observe the or maybe you see the performance of the coating when you do high temperature oxidation study, and usually performance of the coating in terms of the microstructural change, if you would like to see, you will find that on the surface of the coating you will find no signature of the oxidation because that is already oxide layer, and also mentioned you that particular ceramic layer or insulating layer or thermal barrier coating actually does not offer the high temperature oxidation resistance property, but high temperature oxidation resistance property is usually offered by the typical bond coat which you are using for the top coat development, because bond coat offers high temperature oxidation resistance, and as a result of which whatever oxide scale forms, that forms at the interface between the bond coat and top coat. So, you must study the interface very meticulously and measure the thickness of the TGO layer as a function of time and temperature to study the oxidation behavior of this kind of coated alloy. It is very much painstaking job because every time you have to measure the thickness of the oxide layer at the interface, not at the surface. So, this interface looks like that. On the other hand, if you talk about the graded coating, you will find that this TGO layer is not really forming on a single zone, it is forming all throughout the surfaces wherever it faces the bond coat. So, TGO again is formed it is not really continuous layer, it forms at the interface, again it forms at the interface between coating and that of bond coat and that of ceramic layer interface. So, different layers you will get different TGOs formation. So, TGOs, these TGOs actually acts as a kind of again kind of barrier for the subsequent oxidation in case of graded coating as compared to that of monolithic coating. So, if you just measure the kinetics of oxidation for monolithic coating or duplex coating and that of graded coating, you will find that the kinetics of oxidation is much lower in case of graded coating as compared to that of duplex coating for both the temperatures of oxidation like 900 degree as well as 1000 degree. So, you can understand that by the application of the graded coating, the oxidation resistance property could also be improved, which was not earlier known, because the main reason behind the improved oxidation resistance property is that there are a lot of interfaces which are generated because of because of the intermixing and spraying of that ceramic metal mixed layer instead of having only ceramic layer on the top. So, that interfaces play a very important role because it hinders the transportation of the oxidation or acts as a barrier for the oxygen transport, and as a result of which overall kinetics of oxidation increases when you have the typical graded coating as compared to that of duplex coating. So, now if you just see the typical activation energy for oxidation in case of duplex coating and graded coating, you will find that it is in fact much higher than that of duplex coating. So, duplex coating, it was earlier observed that, or it was earlier documented that graded coating would be beneficial for improving the toughness of the coating, but we established that not only toughness, but also high temperature oxidation resistance also increases because of the development of the graded coating in contrast to that of duplex coating. Now, when you found the mass distribution, naturally you will find that in case of duplex coating, that typical mass distributions are like only in 100% duplex coating it is that tetragonal zirconia. On the other hand, in case of after oxidation we get tetragonal zirconia, gamma phase, cobalt oxide, alumina in the oxide scale actually. And similarly, if you see that in case of graded coating, again you will find that in different layer different phases are forming, and this phase distribution is very much dependent on the composition of the each layer. So, but you will find that alumina is forming to a large extent in different layers, which basically acts as a barrier to high temperature oxidation property. Now, if when we just measure the residual stress distribution in the different layer, we found that residual stress also changes to a large extent in case of duplex as well as graded coating. So, you will find that in composition of graded coating, you will find that 100% YSZ residual stress is mostly positive. On the other hand, as we go on increasing the metallic content of the coating, residual stress value just changes from tensile to compressive. So, metallic incorporation actually also helps in reducing the residual stress level, not only reducing the stress level, but also changing the stress value from tensile to compressive. So, this is very much important because residual stress when is compressive, naturally it helps in improving the resistance to thermal fatigue, thermal shock resistance. So, now we propose the mechanism of oxidation, where we propose that the presence of metal oxide at the metal ceramic interface acts as a barrier for counter ionic transportation, and by that process it basically there are also a lot of spinel formation. So, these particular spinel and different oxides help in increasing the kinetic energy of the oxidation, and hence the rate of oxidation decreases to a large extent. So, now we can thus notable conclusions of that work was that the microstructure of the 100% YSZ coating consists of porosities and micro cracks, which help in coating to be strain tolerant. However, the oxygen ingress is there, which leads to oxidation of the bond coat. On the other hand, when you have the combination of co-nicrolia and YSZ, it reduces the quantity of oxygen transported towards the bond coat. Kinetics of growth of TGO is parabolic in nature, and activation energy of duplex, and naturally because of the gradation we could have the higher kinetic energy of the oxidation. And post oxidation analysis showed lot of spinels which actually help in reducing the kinetics of oxidation further, or increases the activation energy of the oxidation, and residual stress also is reduced to a large extent and changes from tensile to compressive because of the graded layer formation. And we also found that the coefficient of thermal expansion and E value increases with increasing the co-nicrolia content, and naturally it helps in reducing the stress level. So, like that we also tried to develop the etiocellulose zirconia and lanthanum mixture, and observe that this composite coating offers superior oxidation resistance property than that of the typical duplex coating. Then another example I will show you, that is coatings for bioimplant application. So, this is a kind of bioactive coating. This was applied on Ti64 substrate. So, Ti64 is a very interesting material for bioimplant application, but problem with the Ti64 is that it is bioinert in nature, as a result of which there is no spontaneous osseointegration on the surface of Ti64, and though it is having lot of applications in different implants, for example, hip and knee joints, bone fixation plates, screws, dental implants, but because of its poor that osseointegration property, usually prior to that Ti64 applying as implant inside the human body, people go for typical hydroxyl apatite coating on the surface by deep coating technique. But problem of the hydroxyl apatite coating by deep coating technique is that this particular coating is very much fragile in nature. So, its durability decreases to a large extent, and hydroxyl apatite gets dissolved gradually, and naturally it reduces the lifetime of the component, particularly whenever it is a kind of fixed implant. So, if we develop the coating by plasma spray deposition technique, naturally the coating will be stronger because it is well adherent to the surface of the substrate, and not only that, because of presence of lot of porosities on the surface, you find that there is more cell adhesion on the surface because of the presence of rough surface. So, it has the possibilities of applications in hip and femoral surface or knee joint surface to a large extent. So, this is typical hydroxyl apatite coating which is very much bioactive in nature. So, usually it is applied on the implant by dipping technique, as I mentioned you. So, that hydroxyl apatite is having that calcium to phosphorus ratio 1.67, which is the indication that hydroxyapatite layer has formed. It is having very good corrosion resistance, it is having very good fracture toughness, porosities are also present which helps in cell adherence, and moreover this is bioactive in nature. So, in this work we tried to have but one of the biggest problem of hydroxyl apatite is that though it is having good fracture toughness, but not adequate actually. So, it is quite low as compared to that of human bone, particularly when you use it for those purpose dynamic implant applications, you should have good fracture toughness. So, there the hydroxyl apatite fails. So, we tried to have the increased toughness of the hydroxyapatite and also increased hardness of the hydroxyapatite by adding titanium dioxide as well as zirconia with hydroxyapatite, and subsequently develop the coating by plasma spray deposition. So, two different types of coatings were applied. Again the composition was earlier attempted, but they did not mention the properties of the coating clearly. So, in one kind of coating we used hydroxyapatite plus 50% titanium, another kind of coating we used hydroxyapatite plus 10% zirconia as a coating precursor, and after this is applied, after application of the coating by plasma spray deposition technique, we tried to see the microstructure phase, wear, corrosion resistance as well as bioactivity. So, this is typical parameters employed for the coating. So, this parameter was the kind of optimum parameter. As I mentioned you, whenever you talk about any deposition technique, it is very important that you say or optimize the parameters properly. So, parameters which play a role in plasma spray deposition, they are the primary gas flow rate, then hydrogen gas flow rate, then carrier gas flow rate, voltage, current, stand off distance, and the velocity of spraying. So, these are the different parameters which play a role in determining the quality of the coating. So, we also did another treatment, that is heat treatment after the coating. So, after the spraying we did different heat treatment. That heat treatment was aimed at retention of the structure of the hydroxyapatite which after spraying it turns into amorphous, but when you do heat treatment it converts from amorphous to crystalline. And also another reason for heat treatment was to release the stress associated with the coating. So, if you see the coating carefully, you will find that the interface is very strong. You will find there is no porosities or no defects at the interface. Coating thickness varied from 200 micron to 250 micron, and in both the cases, even though you are using hydroxyapatite plus titania or hydroxyapatite plus zirconia, you won't really find those features of the titania or zirconia in a separate way. So, they mixed properly and got melted and subsequently sprayed over the surface of the substrate. You can say that there is not many interfaces present between this coating as well as hydroxyapatite and zirconia or titania. So, if you see the structure of the surface, you will find that here there is tricalcium phosphate formation because of decomposition of hydroxyapatite, and calcium titania deposition in case of hydroxyapatite plus titania coating. On the other hand, in hydroxyapatite plus zirconia coating, you will find that there is formation of very fine nano calcium tricalcium zirconate phase formation. So, these were actually evidenced by the transmission electron microscopic analysis. So, whenever you talk about coating, you see the cross section properly, so that you can make sure that coating is adherent to the surface. You can see the microstructure of the cross section as well as microstructure of the top surface properly, so that you make sure what are the phases present, how the microstructure is, because microstructure and composition play a very important role in determining the bioactivity as well as the corrosion behavior of the material. So, that hydroxyapatite plus titania coating, you find that tricalcium in hydroxyapatite plus zirconia coating, you will find that there is formation of calcium zirconate phase, and in addition to that tricalcium phosphate phase. So, if you see the microstructure different characteristics of the coating, you will find that in 50% zirconia as sprayed condition, there is formation of rough surface, roughness increases, but when we did heat treatment of the coating, roughness decreases to a large extent. Heat treatment also helps in reducing the porosity percentage, and also phase composition was also changed because of the heat treatment. As I mentioned you that hydroxyapatite, when you do spraying, it is mostly in amorphous phase, but when you do heat treatment, then naturally the crystallinity increases. So, you get more percentage of hydroxyapatite in the coating. So, this roughness is very important in increasing the cell adherence property, and porosity is also equally important, but porosity content should not be too high, because if it is too high, it reduces the toughness to a large extent. So, you will find that after heat treatment how the properties changes actually. So, this is very important, because if you just go on doing, this is the case for titanium plus hydroxyapatite plus zirconia coating, where you observe that in the coating there are a lot of porosities, and there is also calcium zirconate phase formation, which is nano is in nature, because this phases is the in situ formed product. So, because of its in situ formation, there are a lot of very much nanostructured material on the surface, which was again confirmed by transmission electron microscopic analysis. So, if you see the characteristics of the zirconia coating, you will find that again porosity and that roughness again changes because of heat treatment, and in calcium carbonate in hydroxyapatite plus zirconia coating, you find that the degree of amorphousness actually decreases to a large extent by heat treatment process. So, this is very important, because it is having the final effect on the corrosion resistance property. So, when we measure the wear resistance, we found that because of that typical hydroxyapatite plus zirconia deposition, we get significant enhancement in the corrosion wear resistance property. So, because of the hardness achieved in the coated layer. So, you will find that when we did only hydroxyapatite coating, there we found that hydroxyapatite plus titania coating here, there we found that not much enhancement in the wear resistance was there, but when we did hydroxyapatite plus zirconia coating after heat treatment, we found that that wear resistance increases. So, we could conclude that all coatings are not good for wear resistance applications or wear resistance enhancement. Similarly, we also found that whenever we did like titania coating, titania plus hydroxyapatite coating and titania plus zirconia oxide coating, we found that this composite coating again not so good for improving the corrosion resistance property. But again you can understand that the titanium itself is having very good corrosion resistance. When you add hydroxyapatite, naturally because of the dissolution, the overall oxidation corrosion resistance property decreases, but again the corrosion resistance enhancement was not the main purpose of this study. Main purpose of the study was to have the good fractured, highly fractured surface fracture toughness coating with a very high fracture toughness and coating with high level of bioactiveness. So, finally, we just summarize the different results. We found that the hardness wise, the coating with 50% TiO2 and post heat treatment was having little higher hardness, and but hardness enhancement was more when we added zirconia, and Young's modulus was significantly reduced, and 10% zirconia without heat treatment offered minimum Young's modulus, because for this bioimplant application we do not need very high Young's modulus. In fact, lower the Young's modulus, better is it. Closer is the Young's modulus to that of human bone, better is it. So, by this particular hydroxyapatite coating, the Young's modulus was around 80 to 85 GPa, so which was reduced to 55 GPa. And if you talk about corrosion rate, again corrosion rate was reduced to a large extent, not really to a large extent, but it was higher than that of, it was much lower than that of only hydroxyapatite based coating, and pitting corrosion potential was also not changed to a large extent. So, this kind of coating obviously was not so beneficial in improving the corrosion resistance and wear resistance, though under certain conditions of coating we had very good corrosion resistance as well as very good wear resistance property. But main purpose of the coating was that to increase the bioactivity and have the superior fracture toughness. So, when we did the bioactivity study, we found that bioactivity behavior was reported, or maybe we analyzed the bioactivity behavior of this coating by knowing the percentage of the calcium phosphate deposited when dipped in Hank solution. So, we found that area fraction of apatite formation was increased by this coating, because it is quite natural, because you have hydroxyapatite in the coating, and that particular thing was continued, and we finally tried to optimize the heat treatment parameters and have that optimum composition to be that 10% zirconia after heat treatment, where wear resistance was enhanced as well as the bioactivity was also enhanced. But it is very much important that even though it is improved, but still we were further studies are required to optimize it further, so that we get very tough coating with the required properties as we desire. So, like that, this is a kind of approach which can be followed for the development of the bioactive coating, not only on titanium, but other materials as well, and for corrosion resistance, wear resistance, and also contact fatigue resistance enhancement for bio purpose. And by different studies can be conducted to know the behavior of the coating, performance of the coating to a large extent. So, whenever you deposit any layer on the surface of any substrate for a specific application, it is very important that you do characterize it properly, as well as do testing in different environment to have the result and to know the performance of the coating in the given environment. So, this is a typical application of this particularly bioactive coating in, for example, hip replacement, hip joint replacement, where we found that in the stem section some part is subjected to very much in contact with human blood. So, there the cell adherence rate should be maximum. So, there if you develop this kind of coating naturally, it will promote the cell growth and naturally the implant will succeed for a long time. So, finally, in summary we can say that in this particular 4 talks we discussed about the principle of thermal spray deposition technique, classifications and its scopes, then applications, and finally 2 examples of the application of the thermal spray deposition technique for invention of newer technology or maybe development of newer kind of materials for different applications. Thank you very much.